السلام عليكم ورحمة الله وبركاته. طلاب المرحلة الأولى إن شاء الله زينين. Linear Algebra 2 First Level Lecture 10 Chapter 2 Chapter 1 has finished. Now Chapter 2 Linear Transformation. Introduction about linear transformation. Functions which preserve the structure of a vector space are called linear transformations. That mean functions which preserve in Arabic mean تحافظ the structure تركيب of vector space, the same structure, still the same structure, are called linear transformation. Many important operations in calculus are linear transformation. Definite integral, that mean تكامل غير المحدد. Differentiation, مشتقة. Even taking a limit غاية. Many differential equations can be written as a linear transformation acting on a function space. Linear transformation which are one-to-one and n2 are called isomorphisms. That mean many operations in calculus are linear transformation, definite integrals, differentiation, اشتقاق, even taking a limit, also limit غاية. Many differential equations, معادلات التفاضلية, can be written as a linear transformation. Also, معادلات تفاضلية, differential equation can be written as a linear transformation. A linear transformation in Arabic mean التحويلات الخطية. Linear transformation in Arabic means التحويلات الخطية. This is تحويلات and this is خطية. Acting on a function space. Also this is acting on a function space. Linear transformations which are one-to-one. You know one-to-one from calculus. We talk in the first semester. One-to-one and onto, also you know onto, are called isomorphism. We call linear transformation and with one-to-one and with onto, we call it isomorphism. And this is just in Arabic also we call it isomorphism. Okay, this is enough. Now, examples of linear transformation. Definition. Take definition. Linear transformation. Let V W be two vector spaces. If a mapping L defined from V to W, this domain and this is range, codomain, satisfies number one, L of x plus y is equal to, is equal to L of x plus L of y for all x, y belongs to V. And number two, L of Cx is equal to CL of x for all x belongs to V and C belongs to R, real number. C is real number. Then we say L is a linear transformation. This is page number 1. Now I repeat the definition. Let V and W be two vector spaces. Here, let V and W be two vector spaces. If a mapping, there is a mapping from V into W satisfies two conditions. Condition 1, L of x plus y is equal to, this is equality, is equal to L of x plus L of y for all x, y belongs to V. And L of Cx is equal to CL of x for all x belongs to V and C belongs to R. Then we say L This is L. We say L is a linear transformation. This is important. This is definition of linear transformation. This is definition of linear transformation. Now take example. Example 1. Let L of x, y is equal to x plus 2y. The L defined from R2 into R, because this is R2, input R2 and output. This is input and this is output. Input in R2, two elements, pair of elements, and the output is just one element in R. Now show that L is a linear transformation. Solution. Look, here we have to satisfy this L to these two conditions. First condition, L of x plus y is equal to L of x plus L of y for all x, y belongs to V. And L of cx is equal to C out, move out. Here L move to x and to L here in the first condition. And the second condition, x, C move out of L here, move here from x move from here to here. So this is, we have, if we satisfy this, and this is the first condition, VW, this is vector space and this is vector space, and L satisfy these two conditions, then we say that L a linear transformation. Now this is V and this is W. V also, of course, R2 is a vector space and R, of course, a vector space. We satisfy these two conditions, V and W. Here V R2 and W R, and this is, both of them are vector space. Now we have to satisfy these two conditions. Look, we take let x, y and zw belongs to R2. This is two vectors. Look like this. For any two vectors, here x, y, because this is just definition. And here in R2, I have to this is P1 and this is P2. P1 equal to, because in R2 I have to take pair XY, and P2 also pair ZW, because this is in R2. So this is pair. This is pair. P1 and P2. And the output should be in R. So now I try to make this L of P1 plus P2, this is P1 and this is P2, is equal to, substitute here, this is P1 and this is P2, L of P1 is equal to x plus y, x comma y, this is P1 plus P2, this is ZW, and now try to make to satisfy the first condition. Look here, I can sum these two vectors because this is the summation in R2 defined by, look like this, x plus z and y plus w. This is in R2. And now I have, this is just one pair. This is first argument and this is second argument. X plus y, this is first argument, and y plus w, this is second argument. And here, you know, this is definition, this is the L here, you know, L here. This satisfy x here, and this is satisfy y here. So in our example, L of xy is equal to x. I take x and I take 2y. That means I take first the first argument, x plus z here, because this is x, so I take x plus z. This is first argument because here first argument is x plus z, and plus this is multiplied by 2y, and this is y, so 2y plus w. And now we can move, this is 2 here, and this is x plus z plus 2y plus 2w, and change this is equal to x plus 2y. So move here, this is move here 2y, and this is move here 2y, move here x plus 2y plus z plus 2w. And now you know this is equal to, and this is equal to L of xy. This is equal to L of xy because L of xy, first argument the same and the second multiplied by 2. So this is also, this is the same x and this is multiplied by 2. So make back. This is equal back. And this is plus L of, also this is z the same, just z and the 2w, so this is w. Also come back x plus 2y, and this is z plus 2w, so this is zw. And now this is equal to L of p1, this is p1 because this is p1, and this is also p2 from definition in the at the beginning. This is L of p2. So now we satisfy the first condition. This is the first condition. L of p1 plus p2 is equal to L of p1 plus L of p2. Sorry, this is p2. This is p2. L of p1 plus p2 is equal to L of p1 plus L of p2. And this is from definition. Here, L of x plus y is equal to L of x plus L of y. Now, second condition. Second condition. L of C P1. We take P1. We need in the second condition just 1 point. We don't need 2 points. In the first condition we need 2 points. We don't need C. And the second condition we need C and C in R and P1 in R2. This is equal to, this is equal to L of C, and P1 is equal to xy. And this is from definition, move here C, from definition multiply scalar multiplication, move here in x, move to Cx and Cy. This is the scalar multiplication. And this is the first argument. This is some this addition in R2, and this is scalar multiplication in R2. And now this is from definition of L2. The first argument is still the same. The first argument here, what? Cx. So we write here Cx plus 2 second argument. And here, what about second argument? Cy. And so this is C2Cy. And this is 2Cy. And now we can C move from here and here. C, this is still x plus 2y. And this is equal to, and C move here, C, and this is L of x, y by definition. Here. This is equal L of x, y. Now this is equal to P. This is x, y. So this is C L of P1. So now we satisfy the second condition. This is second condition. LCx is equal to CL of x, and here LCP1 is equal to CL of P1. So this is this is for all P1, P2 belongs to R2 and C belongs to R. This is true for all. Therefore, L is a linear transformation. Is a linear transformation. This is page number 2. I think this is clear. Now try to take another example. Example 2. This is 2. Let A belongs to Rm times n. This is matrix Mn, m rows and m columns and m n rows, and define L from Rn times 1 into R m times 1 by L of x. L of x is equal to a x for each x belongs to Rn times 1. Show that L is a linear transformation. Solution. Now look, now A is a matrix from belongs to Rmn times n. We define L and define L from Rn times 1 to into Rm times 1 by L of x equal to, this is definition of L. L of x is equal to Ax, a matrix, we see. And this is x belongs to Rn times 1, because this is defined from R, so this is input and this is output. This is input and this is output. This is input and this is output. So this is any vector. Here in an input, this is input and this is output. In input, x belongs to Rn times 1, and the output belongs to Rm times 1. Solution: let x, y belongs to Rn times 1 and c belongs to R. This is in R. Now we write L of x plus L of x plus y. This is x, this is y, is equal to, by definition, ax, that means ax plus y. This is by definition here, not just x plus y, and this is by definition ax, and so here ax plus y, because this is here x plus y, and this is from definition of matrix. This is move here ax plus a y, and this is by definition what equal to L of x, because this is here, and this is plus L of y. So we satisfy, this is first condition. This is first condition. L of x plus y is equal to L of x plus L of y. Also, second condition, L of cx is equal to a cx, because here cx and this is ax, so this is acx. This is, we can move c out, equal to, by definition of matrix, cax, and this is equal to c the same, and this is equal to L of x by definition. Thus L is a linear transformation. L is a linear transformation. This is, I think this is easy. Now we take example 3. Define L from Rm times n into Rn times m. Opposite here m times Rm times n, and here Rn times m. By, defined by L of A is equal to A transpose. You know what about transpose? L of A, this is matrix L, A, this is input and this is output. This is input here Rm n, and this is output here, because this is will be rotate. Show that L is a linear transformation. Now, solution: let A, B belongs to R m times n, and C belongs to R. This is scalar constant. Number 1, L of A plus B, this is first condition, is equal to, this is definition, L of A equal A tan AT, and here we have input A plus B, so this is that means A plus B T transpose, because this is here input A plus B, not just A. This is here just A, and this is AP, so this is here. Now we know the first semester this T move here and here, so this is equal to A transpose plus B transpose, and this is equal L of A plus L of B. So I satisfy the first condition. L of AB is equal to L of A plus L of B. So you know that the first condition and second condition, L of CA is equal to also here CA transpose, and from definition of transpose of matrix, this is will be equal to CA transpose. So this is equal to CL of A. Also this is satisfy the second condition. Thus L is a linear transformation. Linear transformation, and this is example is finished. This is page number 3, and now we take example 4. Let VW be two vector spaces and L defined from V into L into W, defined by L of X is equal to 0. Is equal to what? 0. For all X belongs to V, because this is input and this is output in W. Show that L is a linear transformation. Solution. Let X, Y belongs to V and C belongs to R. Now we try to satisfy two conditions. The first condition, L of X plus Y is equal to what? L of XY. Here. In our example, L of X equals 0 if X plus Y also equals 0. Also equals 0. And this is 0 is equal to, 0 plus 0. Right? And this is 0 is equal to L of X, and this is 0, I can write it L of Y. So I get L of X plus Y is equal to L of X and L of Y. So this is first condition. Now second condition, I think the same. L of CX is equal to also 0. Everything here will be output will be the 0. And this is 0 is equal to C times 0, right? This is 0, C times 0 also 0, and this is 0 is equal to, this is equal to C, this is 0 equal L of X, right? So we satisfy the second condition, and thus L is a linear transformation. This is linear transformation known as the trivial transformation. This is now linear transformation, now trivial transformation. And also another example 5. Let L defined from V into V, where V is a vector space. Be defined by L of X is equal to X, the same, still the same, X here. Show that L is a linear transformation. This is page number 4, and try to do it here. This is solution. L of let X Y belongs to V. Here the same, input output the same, you know, look here, L from V into V, put the same, will be still the same. X Y belongs to V, C belongs to R, in R the output. So now the first condition, try to satisfy the first condition, L of X plus Y, this is equal to, here in the definition L of X is still the same, X, and here L of X plus Y, so this is still the same, X plus Y. This is by definition of, this is example, L of X equal X, and here L of XY plus Y, this is equal X plus Y, and this is equal to, this is X equal L of X, and this is y is equal to, so this is plus here plus L of y. So we satisfy the first condition. And the second condition, L of cx is equal to cx, and this is equal to L of x. So this is L of cx. Thus L is a linear transformation. We call this linear transformation the identity function. The identity function. We call it identity function on a vector space. We call this is because this is same, because this is still the same. L of x equal x, so this is, we call it identity function on a vector space. Identity function on a vector space. Now we take another example, example 5. This is example 5. Define, this is example 5. Define L from C0 of R into R. And this is function, integrable function by L of f, this f here function is equal to integral from 0 to 1. This is the finite تكامل محدد f of x dx. And this is continuous function in R. This is space continuous function in R, and show that L is a linear transformation. Solution here. Let fg, this two function, belongs to C of R, and C belongs to R. This is real number, here's scalar. And the first condition, L of f plus g is equal to integral from 0 into 1 f plus g dx. This is equal to here f of x, of course, from integral from 0 to 1 f of x plus g of x dx. And of course the integral can move here and here. This is equal to integral move here and here. Integral from 0 to 1 f of x dx plus integral from 0 to 1 g of x dx. And this is equal to, this is what equal to L of f plus, and this is equal L of g. So I satisfy the first condition. L of f plus g is equal to L of f plus L of g. And second condition, L of cf, this is equal integral from 0 to 1 cf dx, and this is equal to, this is constant, right? This is equal to cf of x dx, and this is equal, can move c here out of integral because this is constant, integral from 0 to 1 f of x dx, and this is equal, what about this? This is equal L of f. So this is equal c the same, and this is L of f, and this is the second, exactly this is the second condition. Thus L is a linear transformation. This is page number 5. And also another example is example 6. Let L defined from C1, this is differentiable, first differentiation, first derivative الاشتقة الأولى, into C of 0 of R. This is continuous function. Be defined by L of f of x is equal to f prime of x. This is derivative. F prime of x. Show that L is a linear transformation. Solution. Let f g belongs to C1 of R and C belongs to R. This is the same. Every example the same. Every example the same. We take two elements in the domain and C constant, one constant in R. The same. And try to satisfy two conditions. The first condition, L of f plus g, here x, because this is the definition, is equal to, by definition, this is here f plus g, so this is f plus g prime. Prime, this is derivative here, just f, so here derivative in at f, and here f plus g, so this is the on prime on f and plus g. And we know from calculus the derivative move here and here, move to the sum. So this is equal to f prime of x plus g prime of x, and this is equal to, from definition, L of f of x plus L of g of x. This is equal L of f, and this is equal L of g. This is first condition. L of f plus g is equal to L of f plus L of g. And the second, L of cf of x is equal to, and here cf, so this is cf prime of x, and from definition, from calculus, we know the derivative move here just on function. This is function, this is constant, so out, move out. This is equal to c f prime of x, and of course this is equal to L of, this is equal to c the same, and this is L of f of x. So we satisfy the second condition. Thus L is a linear transformation. Now we take another example. This is example 6. This is example 6. And now we take example 7. Example 7. Let L from R2 into R be defined by L of x, y is equal to x squared plus y squared. Is L a linear transformation? Show that. Here, question mark. Now try to if L has two, if L is satisfy condition 1 and condition 2, then we call it linear transformation. If one of these two conditions not satisfied, so we call it not linear transformation. So this has to satisfy two conditions. If one of them not satisfied, so directly we say this not linear transformation. We can solve this question. Look, let xy belongs to R2 and c belongs to R. This is real number. Now L of c of xy, L of c of xy, the c move here and here is equal to L of cx cy, and this is by definition. What about this? This is here the first argument square and the second argument square, and here the first argument cx, both of them square, and here the second argument cy, also both of them square, and this is equal to c square x square plus c square y square. Move here, move square to c and x, and here also move to c and y. So we can now take this is here, and this is x plus x square plus y square. This is x square plus y square, and this is equal to, and now this is equal c square L of x y. You know what we get? L of c x y, L of c x y is equal to c square L of xy. So this is not c. No, if this condition satisfy, we have to show that L of cxy equal to c, just c, not c square, c L of xy. But what we get? We get c square L of xy. So this is which implies L of cxy is not equal to c L of xy. Thus, this is page number 6. Thus, L is not linear transformation. You know that? And also example, say 8. Example 8. Let T from R n times n, this is matrix, into R. Be defined by here T. No, doesn't mean T or L, the same. T of A is equal to determinant of A. T of A is equal to determinant of A. A is a matrix where A belongs to R n times n. Now the question is T a linear transformation? The question mark here show that. Solution. You know determinant from the first semester. Of course, you know it. You remind. Let AB belongs to Rn times n and C belongs to R. Now try to satisfy the first condition. L of AB plus B is equal to here T. Here our example T of A plus B is equal to, this is equal to determinant of A plus B. And we know from the first semester this is not equal to always, is not equal to determinant of A plus determinant of B. We know from the first semester determinant of matrix, sum of two matrices is not equal to determinant the first and plus determinant of the second. In general. In general. Also, we know that determinant of CA is equal to C power n determinant A. Determinant A. From the first semester, you know this, because this is condition 2. In this example, both of two conditions not satisfied. The first condition, we didn't get the equality here, and this is, you know, this is not equal. This is not will be not equal T of A plus T of B. And here also determinant of CA is not equal. This is not equal to C determinant of A, because here C power n, because here C power n determinant A, not C determinant A. So thus T is not linear transformation. You know that? So I think this is enough for today. Thank you very much. Goodbye. This is page number 7. I think this is page number. Okay, thank you very much. Goodbye.